Part of the reason for all of the, wait, almost blew that. Got to get, wait, I've already got it started. Okay. All right. I did it right. All right. All right. Part of the reason for all the craziness is we've just started the second mini-term. And someone had added a math course to the schedule at a time that was not regular, normal. So it conflicts with other times. But the class made, barely, but made. But now finding an instructor who can teach it is just about impossible because it's not starting at a good time. People are in class when it started, or will be starting. And so I have been, for the last 2 weeks, putting off other things, trying to find someone to teach this class. I think I may have worked it out this morning, but I'm not sure until I get an email back from somebody. But anyway, it's just been nuts. So my office hours may be changing, or they may not. Okay, it's really nuts. Today, my second mini-term class, my first mini-term class started at 1:15. Second mini-term class was scheduled for 3:15 because the automotive program needed it. Well, they decided to change their schedules, so they don't need it now. So now I'm starting a class later than I want to start because of them, but they're not in it. So I'm going to see, but today I've got to meet it at the time it was scheduled. But starting with today, I might be able to move it earlier. So I won't know what time my office hours will be on Tuesday and Thursday until I meet with them today. I should know by Thursday. But today also, I've got to meet with that math class that doesn't have an instructor up until the time my other class starts. So, but I think I found someone who hopefully can teach the class, but she's the one that's in another class, and we're trying to find a different instructor for that one. That's an orientation class. So we're trying to work that out. And so today I know after this class is over, I'll be in the office until 2. Normally it was 1:15. Now it'll be 2. Thursday, it might be back to 1:15, it might be 2, or it might be 3:15. I don't know what time it'll be, but I should know by Thursday. All right. Another thing is I will be submitting midterm progress reports tomorrow, but I've got something for you and for Keyston. I don't have anything for Peyton yet, so hopefully you'll be getting me something. On the Thursday, the 17th, is Miss Lawson State Coordination. That's at the Bessemer Civic Center right next door at 7 o'clock. Okay. So those are the announcements from the administrative calendar. The volleyball team has a match today versus Southern Union, but unfortunately that's down in Wadley, Alabama. So if you happen to be driving by there at 6 o'clock, stop in and cheer the team to victory. Okay? I'll tell you the rest of those next time. And if you are interested in the NASA's Community College Aerospace Scholars Program, tomorrow is the deadline for submitting an application. So be sure you get it in by tomorrow. I have as much information as I got right here on this piece of paper. You're welcome to it. I won't be announcing it after tomorrow. And tomorrow may be even too late then. Any questions on anything we've done so far? Okay. Now, where we left off last time is in Chapter 2, Matrices, 2.4 Elementary Matrices, and you weren't here for it, so I'll try to fill in what I can. Were you able? Oh, you did watch it. Okay, good. Okay. All right, so here's what it says. This is example 4, top of page 78. Find a sequence of elementary matrices whose product is the non-singular matrix A. Well, here's the A that we're going for. Okay, let me get my pen set up. A is equal to simple matrix, -1, -2, 3, 8. All right. And you'll be so glad they started us with a 2 by 2. it's going to be enough, okay? Now, I'm going to try to do this. The book does it one way, and I'm going to do it also. But I'm going to add another sort of step into it, okay? So that's where we're starting. And we're wanting to row reduce this matrix to get it to the identity matrix, okay? Because for every step we do to row reduce this, we are going to develop an elementary matrix that does the same thing, okay? And the reason we do that is then we do the inverse of that elementary matrix. That's going to be the sequence of elementary matrices whose product is this one. So this is really a little convoluted, but it kind of makes sense. Okay. First thing we've got to do to get this in reduced row echelon form is what? If you don't want to talk, you don't have to. Okay. Yeah, you're trying to row reduce this. So first thing we want to do is make that -1 a +1. So you do that by minus row 1 becomes the new row 1. So multiply the top row by -1. So let's do that. Now, here is your identity matrix, 1, 0, 0, 1. Now we're going to keep coming back to that matrix, not, okay. So this is the I2, okay. That sort of matches that. So what we're going to do here is multiply the top row by -1. So that becomes 1, 2, 3, 8, right? Okay. We're going to do the same thing here. Minus row 1 becomes the new row 1, okay? So I'm going to call this E1, okay? And E1 is going to then be, do the same thing to that. -1, 0, 0, 1, okay? Now, what we also want to do is E1 inverse, the inverse of E1. Now, if you remember that, I don't know if you remember this from let's flip back one page, and when you are multiplying on the previous page 77, oh, you don't have that, okay, okay, to how you undo how you do the inverse of an elementary matrix that you've multiplied by is multiplied by its reciprocal, okay? Well, the reciprocal of -1 is -1. So that inverse of this matrix is -1, 0, 0, 1. It's the same thing, okay? Now, here's how you test this. If you were to multiply these two together, you need to get to that. So let's see if it does. 1, 0, that's a 1. 0, 0, that's a 0. 0, 0, that's a 0. 0, 1, that's a 1. Yeah, that works. So that's the inverse of this matrix. It's the same matrix, okay? But it gets you back to this, okay? Now, all right. What's the next step here to get this into our matrix A? Go back to the A. What's the next step that you want to do? You want what's underneath that leading 1 to be a 0. So therefore, you're going to multiply this by -3 and add to that, right? So -3, row 1 plus row 2. That becomes the new, oh, I put it in the wrong place. That becomes the new row 2. I should have put it down here. Sorry about that. Well, now here, so let's do that, okay? So we're leaving row 1 alone, 1, 2, and the new row 2 will be -3 times 1 is -3 plus 3 is 0. -3 times 2 is minus 6 plus 8 is 2. All right. Now, our E2, now we don't use E1. Do not use E1. Go back to your identity matrix. And we're going to do the same thing we did to this one, to the identity matrix. So that's minus 3, row 1, plus row 2. That's the new row 2. Okay? So let's do it here. We're using the top row, so leave it alone, 1, 0. We go back to the identity matrix. Okay, the new row 2 is going to be minus 3 times 1. That's minus 3 plus 0 is minus 3. And minus 3 times 0 is 0 plus 1 is 1. Okay. Now we do the inverse of this E2. Yep. Inverse of E2. Now, you don't have your book, but for those who do, flip back a page, and how you do the inverse of this elementary row operation is how we got E2 was row 2 plus minus 2 minus 3 row 1. I'm sorry. Row 2 plus minus 3 row 1 is the new row 2. Okay, they're saying it slightly different than I did. So how you undo that is multiply by plus 3. So this will be, let me put the I2 here again. That might be helpful. Okay, for that first one, we did the same thing, just to get it back to where it was. Okay, multiply by reciprocal. Okay, this is 1, 0, 0, 1. Okay, this time we're going to do plus 3 row 1 plus row 2 is the new row 2. Okay, that's what we do to do down here. Okay, so that's going to be 1, 0, top row stays the same, and that would be 3, 1. So that's the inverse of that one. Okay. Yeah. Okay. Now, again, the test for it to see if it's right is do your multiplication. This should give you that, because when you multiply any matrix by its inverse, you should get the identity matrix. So let's see. 1, 0, that's 1. Good. 0, 0, that's 0. Got it. Then this one is negative 3 plus 3, 0, and 0, 1. Yeah, that does. So yeah, that's perfect. It's exactly what we want. All right, the next step is on this one, and here we do use the previous matrix. You do row 2 divided by 2, because what you want next is a 1 down there, right? Okay, so divide by 2, and that's the new row 2. All right, so that gives us 1, 2, 0, 1. Okay, now we do the same thing up here. Now I'm going to start erasing here because it just gets too muddy, murky here if you just keep all those things in place. So here it's going to be row 2 divided by 2 is the new row 2. Just like we did there, and that then gives us E3, which is, we're leaving the top row alone, just like we left the top row alone here, 1, 0, and the bottom row becomes 0, 1/2. All right. Now, how do you undo that? E3 to the minus 1, the inverse of E3. How do you undo that? Well, this is a lot like what we just did, only this time it's multiplied by the reciprocal. Remember, that's what we did before, just happened to be the reciprocal of minus 1 was minus 1. Reciprocal of 1/2 is 2. So that's going to be, so let me erase that. So the corresponding thing we're going to be doing here, this is going to a different one, is going to be 2 times row 2 is the new row 2. You multiply by the reciprocal. Here you multiply by 1/2, here you multiply by 2 over 1. Okay, so that would be 1, 0, leave the top row alone, 0, 2. Okay, now again, if you need to check it just to see if it works, let's do 1 plus 0 is 1. Yes, fine. 0 plus 0 is 0. Yes, fine. 0 plus 0 is 0. Yes. And 0 plus 1 is 1. Yes, that gives us exactly like we expect. All right. The last step to get this to reduced row echelon form is to minus 2 row 2 plus row 1. You want that 2 to become a 0, right? All right, so let's do it. Using row 2, 0, 1, and minus 2 times 0 is 0 plus 1 is 1. Minus 2 times 1 is minus 2 plus 2 is 0. Yes, that's exactly what we wanted there. The E4 that we have here, we're now, I'll put it up here. Okay, how do we undo that row operation? It's a lot like we undid this one that we've already erased now. You multiply by the opposite of it. So this will be a plus 2 row 2 plus row 1. 2 row 2 plus row 1. All right. So leave the, now again, you're using the identity matrix. So leave the bottom row alone, just like we did here, 0, 1. And then we do 2 times 0 is 0 plus 1 is 1. And 2 times 1 is 2 plus 0 is 2. Okay? Now, no, I'm sorry. Wait. Minus 2. We do the same thing here that we did there. I was doing the inverse. Same thing here we did there. So that gives you a minus 2 there. Okay? Now, this is what I had jumped ahead to. E4 inverse, that's the one that's 1, 2. That's the plus 2, row 2 plus row 1 is the new row 1. And that's your 0, 1. Now again, to check it, ooh, goodness, that hurt. I injured my knee a little this weekend, so every side motion hurts. So, okay, 1, 0, that's 1. 2 minus 2, that's 0. 0, 0, that's 0. 0, 1, that's all. Yeah, that works. Okay, so that does check exactly like it's supposed to. So, this is bizarre but true. We started with this. We row reduced it. We mirrored the operations we're doing in row reducing this to elementary rows, elementary matrices, doing it to the original identity matrix here. So these are all elementary matrices corresponding to the same steps we did here, but we did these to this, not, yeah. So, and at the same time, we did the inverse operations to get the inverses of the elementary matrix, and we've got it. Now, okay, so we step this down, doing the operations to the identity matrix, doing the inverse operations of the identity matrix, we got these. Now, here's what we do now. We did these in order, E1, E2, E3, E4. To come up, to get back to here, we start with E4, E3 inverse, E4 inverse, E3 inverse, E2, yeah. And we go backwards. We don't do that. We just do those. So, here's what we claim to be the case. I'll do it the same way they did. We claim that our matrix A should be in reverse order E1 inverse E2. I'm probably not writing this right. Probably shouldn't put the brackets around those. I'm just running out of room. I was trying to consolidate. Okay. E1 inverse, E2 inverse, E3 inverse, and E4 inverse. Okay. So that's -1, 0, 0, 1. 1, 0, 3, 1. 1, 0, 0, 2. And 1, 2, 0, 1. Okay. Now, it doesn't really matter which order you do these, okay? And I kind of hate to do this, but I need more room, so I'm going to erase the stuff at the top. It's okay? You got all the steps down there. So if I have botched something up really badly, you're going to straighten it out. Okay. I don't think I need this either. Or that. Or this. I hope I copied them right. Because remember, while multiplication of matrices is not commutative, it is associative. Okay? So we can do these in any order we want to. This may be the first day Keyston's missed. I wonder if he's got the cold now. Sure hope I don't get it. I'm hoping to get my flu shot Friday.
Yeah, I couldn't get mine. I was too sick. They wouldn't give it to me.
Yeah.
I got too much going on, so
All right. So let's see what happens if we multiply these two together, these four together. All right, so let's start with this one. -1, 0, 0, 1. All right, we're just talking about you, hoping you hadn't gotten sick. He's been sick. Oh, look at this. He's going to come in coughing.
My chest, right? I'm not sick.
Okay. Oh, sorry. Okay. We're doing example 4 at the top of 78, and we're going to verify it by multiplying these things together. There's your E1 inverse times E2 inverse, which is 1, 0, 3, 1. Okay, so let's do that one first. It's going to be a 2 by 2, so let's multiply. -1 plus 0 is -1. 0 plus 0 is 0. Now catch me if I'm wrong here. 0 plus 3 is 3, and 0 plus 1 is 1. Okay? We're going to multiply that by 1, 0, 0, 2. Okay? That's also going to be a 2 by 2. Okay, let's do that. -1, 0, that's -1. 0, 0, that's still a 0. 3 plus 0 is 3, and 0 plus 2 is 2. And then we're going to multiply that by E4, which is 1, 2, 0, 1. All right. I don't think I have room over there, so I'm going to do it down here. That will be a 2 by 2. That's -1 plus 0 is -1. So far, so good. Then you got -2, -2. So far, so good. Then you got 3 plus 0 is 3. So far, so good. And then you got 6 plus 2 is 8. Look at that. That's the same as A. So sure enough, now Keystone will fill you in on what we did. We took that matrix and started row reducing it. Now, I did it on the board like this, but I've just erased it before you came in. Sorry about that. We did the row reduction of that to get down to the identity matrix. We started with an identity matrix here, and every step we did here, we did an elementary matrix with that same step. Then when we went from this one to that one, we went back to the identity matrix and did it, the same step there, and then did that. So we came up with 4 elementary matrices using the same steps we did here to row reduce this. And at the same time, as soon as we got this elementary matrix, we then did its inverse, as we did last time on the previous page. The inverse of the elementary matrix, inverse of the element, inverse of this. We had 4 of them. These were those 4 inverses, okay? And whereas we started with E1, E2, E3, E4, we do E1 inverse, E2 inverse, E3 inverse, E4 inverse in that order, and we just found out that when you multiply those together, really in any order, you get that same matrix. Okay? So, we have shown that. That was a Gauss, okay. Back in section 2.3, we found an inverse by Gauss-Jordan elimination. If you want to do the same thing here, you can find the inverse by excuse me. To get the inverse of matrix A, now I've already erased these so I can't show them to you, but the inverse of matrix A inverse, would then be take the elementary matrices we came up with to row reduce A and multiply those in reverse order. So you would have done E4 times E3 times E2 times E1, okay? And I've already erased them, so I can't go back and reproduce them, but that would give it to you. And that should give you the inverse matrix of that one. These are the inverses of those. Actually, we could do them just by doing the inverses. That would be a 1 minus 2, 0, 1. That's the inverse of E4 inverse at the bottom. Okay, that would be that one. E3 would be 1, 0, 0, 1 half. E2 would be 1, 0, minus 3, 1. And E1 was just same as E1 inverse, minus 1, 0, just because its reciprocal is the same. Okay. So if we multiply those 4 together, we should get A inverse. Well, let's see if we do. Ugh. Okay. Let's do the first 2 together here, and that'll give us a 2 by 2. And that'll be a 1. That'll be a 0, minus 1. That'll be a 0, 0. And that'll be a 0, 1 half. Okay? Then multiply that by E2, 1, 0, minus 3, 1. And that gives us a 1 plus 3 is 4, 0, minus 1, 0, minus 3 halves, I'm not liking this, and 0, 1 half. Okay? And then multiply that by E1, which is minus 1, 0, 0, 1. I'm doing these fast, so I hope I'm not making mistakes. Okay? That would be a minus 4, 0, that's a minus 4, 0, minus 1, 3 halves, 1 half. Okay. Now that's supposed to be the inverse of A. Now they didn't do this in the book. I'm just checking to see if what they said was true. But how can we do the inverse of A? Remember, it really wasn't too bad. It's a 2 by 2. What is A inverse? Remember that little trick we did? First, find the determinant. That would be a minus 8 plus 6 would be a minus 2. Okay? Determinant of A would be, what did I say, a minus 2? Right? Okay. And then the inverse of this would be 1 over a minus 2, which is minus 1 half. Okay. Times, and then remember what we did? We reversed the main diagonal and made it 8 minus 1, and then we negated the others, minus 3, 2. All right, and what does that give us? Negative 1 half times 8 would be a negative 4. Negative 1 half times 2 would be a negative 1. Negative 1 half times negative 3 would be a 3 halves. And negative 1 half times a negative 1 would be a 1 half. Okay, what do we get? Oh my goodness, look at that. They are the same. That's a lot easier. Okay, why would you ever do it this way? You wouldn't, but this is just building the theory that this does work. Okay, so, wow. Okay, now, of course, if A is a singular matrix, meaning it doesn't have, its determinant is 0, you can't do it. You can't, it doesn't have an inverse, so this procedure wouldn't work there. All right, so let's then go to Theorem 215, bottom of the page. Is it all right for me to erase this, or you want to hang it up there a little bit longer? You all right? Okay. Okay, here is Theorem 215, equivalent conditions. Now, we started this earlier. We're going to be adding to it periodically. Here's another addition to it. These are equivalent conditions. We're starting with A is an n by n matrix. Of course, that means it's square. Okay? If A is an n by n matrix, then the following statements are equivalent. Okay, following statements are equivalent. Number 1, A is invertible. Okay. Of course, if A was not a square matrix, you couldn't possibly be invertible. But even being a square matrix, it may not be invertible. Okay? This is saying if A is invertible, then all the rest of these are true. But it's also saying if any one of these is true, then this is true. Okay, so the second equivalent statement. AX equal B, if that's a true statement, it has a unique solution for every n by 1 column matrix B. can call it a matrix or a vector. Okay. It has a unique solution. No matter what B you put out there, you'll get a unique solution. One and only one solution. Okay? 3. Another equivalent statement. If you have AX equals 0, and that I think has to be a vector 0. Okay, 0 vector. I don't think you just want the number there. It has only the trivial solution. Now that follows just from the one above it, because if this, for any matrix B, including the 0 matrix, there has to be only a unique solution. Well, one solution for this is always the trivial solution, so that means that's the only solution. None of the other solution will work for that. Okay? Number 4, another equivalent equation to that. A is rho equivalent to I sub f. The n by n. Okay? Yeah. That's how we went about doing inverses before. So if it has an inverse, you do the row equivalent, row reduction, you get the identity matrix. Okay, 5. And therefore, if you can do that, A is invertible. Number 5. A can be written as a product of elementary matrices. Okay, we just did that one. Any invertible matrix can be written as a product of elementary matrices. Okay? Long process to get it, but you can do it. Okay? And it's not a hard process, it's just long. All right. So those are your 5 equivalent conditions here. All right, to erase. And we'll keep adding to them. In the next chapter, we'll now have 6, and maybe even 7. We'll keep adding to those. All right. Now we're going to do something new. At the heart of the most efficient and modern algorithms for solving linear systems, AX plus B, AX equal B, I said plus, but equal B, is the LU factorization. The heart of the most efficient modern algorithms for solving those kind of equations is the LU factorization. What in the world is that? Okay? In which a matrix A is first expressed as is expressed as a product of an L times a U. That's why it's called the LU factorization. Now, what does L and U stand for? L stands for lower triangular matrix. Okay. U stands for, guess what? Upper triangular matrix. Okay? Now, all right. Now, here's what we mean by those two things. A lower triangular matrix will look like this. I'm going to write it in 3 by 3, but any size would do. A11, 0, 0. A21, A22, 0. A31, A32, A33, done. That is a 3 by 3 lower triangular matrix. What that means, the main diagonal can be any numbers in the world. Any numbers. I want to say except 0, okay? We'll get back to that later, but let's right now just leave it general and say any numbers in the world. Below that diagonal, you have other numbers, any numbers in the world. But above that diagonal, you can have only zeros, okay? Then your upper triangular matrix, it would read like this. A11, A12, A13, 0, A22, A23, 0, 0, A33. And again, the main diagonal can be any numbers in the world. I want to say not 0, but we'll right now say any numbers in the world. The entries above that diagonal can be any numbers in the world. Below, you have to have zeros, all zeros. So 0, 0, 0. Okay. That's what we mean by an upper triangular matrix. This is an ugly 0 there, so I just made it look better. All right. So here's the definition of an LU factorization. If the n by n matrix A can be written as a product of a lower triangular matrix and an upper triangular matrix okay, then A is equal to LU, that's the product of those two, is an LU factorization of A. Okay. Sort of dumb seeming. A is equal LU. LU is the LU factorization of A. To say A is equal to that, say A is an LU factorization of A. It's not. The LU is. Okay. But that LU is the LU factorization. There's not many times you can factor a matrix. This is how you can. If you can. Okay? So, let's do example 5. They haven't told us how to do it yet, by the way. They just said, if it exists, this is it. So, without knowing how they came up with these, let's hit it. Here is a matrix, 1, 2, 1, 0. So my statement about the main diagonal can't be zeros. Yeah, they can. Okay? Now, what they claim here is that this is a product of 1, 0, 1, 1. What kind of matrix is that? That's a lower triangular, because the main diagonal is 1, 1. The upper is 0. Above that is 0. Times 1, 2, 0, negative 2. What kind is that? Upper. That's the upper triangle matrix, because below the diagonal, which is just 1, 2, is a 0. Okay? Now, this would be your L, this would be your U. Let's just check that and make sure they're not blowing smoke at us, right? Okay? They are known to do that, right? We have not. Okay, let's do 1 plus 0 is 1. Sure, that works. 2 minus 2. Whoa. 2 plus 0 is 2. Okay. Woo. 1 plus 0 is 1. And 2 minus 2 is 0. Yep, that is, this product yields that. And that's a lower times an upper. So that's your LU factorization. Now, this is going to take a little more effort and a little more space, but it's still not too bad. Here's your next A. The first one they didn't say it was A, but it was, okay. And that is 1 minus 3, 0, 0, 1, 3, 2, negative 10, 2. They claim that is the product of 1, 0, 0, 0, 1, 0, 2, negative 4, 1. Times 1, negative 3, 0, 0, 1, 3, 0, 0, 14. Now, sorry, just burning dry. Has something to do with the air coming off my computer, but whatever. All right. What kind of matrix is this? Lower triangular? Upper triangular. So if indeed these two multiply to be that one, this is the LU factorization for that matrix. Let's see if it does. Okay? Oh my. Okay. 1, 0, 0 was a 1. Negative 3, 0, 0, negative 3. 0, 0, 0, 0. So far, so good. 0, 0, 0, 0. 0, 1, 0, 1. 0, 3, 0, 3. Okay? 2, 0, 0, 2. Negative 6, negative 4 is negative 10, plus 0 is negative 10. And 0, negative 12, plus 14, 2. Yeah, sure enough, this is an LU factorization of this matrix A. Hey, Joy, fine. How in the world do we get those things? They haven't told us that yet. Before we do, there's a little green blob at the bottom of page 79, Linear Algebra Applied, Computational Fluid Dynamics, CFD, computer-based analysis of such real-life phenomena as fluid flow, heat transfer, chemical reactions, and solving the conservation of energy, mass, momentum equations involved in CFD, computational fluid dynamics analysis, can involve a large system of linear equations. So for efficiency in computing, the CFD analysis often uses matrix partitioning and LU factorization in their algorithms. Aerospace companies such as Boeing and Airbus have used CFD analysis in aircraft design because fluid dynamics, that's the passage of air over the fuselage of a plane. And if they don't get that right, you got problems. Anyone ever hear of the Boeing, what is it, 370 something another Dreamliner?
Yeah, actually the software, it didn't, it was some kind of relay mission supposed to the engine. And then they grew up and all the pilots supposed to kick in and kick off.
Yeah. Basically, the whole reason for that mess is they adjusted something on the fuselage. And when they did, that changed the dynamics. So then they started making patches to the computer program to try to catch up with that, and it just got into a tangled ball of worms, okay? They still haven't gotten it worked out, have they? Yeah. Every solution they've come up with so far, I think, has failed some sort of a test. And it's all because they started monkeying with it, probably without doing this.
Yeah, it's kind of odd because the first thing they should have done was do like a so-called automatic recall
Uh-huh.
and just pull every plane that they made an adjustment to.
Yeah.
Pretty much fix it.
Yeah.
You know, but those planes were like international. Like, they did all
Oh, yeah.
that kind of thing, so,
Everybody was wanting to buy them.
yeah.
And sometimes they did okay, but every now and then they didn't. So I don't know. Maybe they did do this, but my guess is they didn't do it thoroughly enough. Someone skipped some steps or something. So, if a square matrix A row reduces to an upper triangular matrix U using only the row operations of adding a multiple of one row to another row below it, then it is relatively easy to find the LU factorization of the matrix. All you need to do is keep track of the individual row operations shown in the following example. So this is going to be the same matrix A that we have here, and we're going to walk through what they did to get it. Okay? So I think I'll start over with a fresh sheet. I hate to rewrite that, but I think I'm going to need all the room I can get. So here's matrix A, same one we just had down there. We know it has that factorization. We just did it. Okay? 1, -3, 0, 0, 1, 3, and 2, -10, 2. All right. What we want to do is find the LU factorization for that matrix A. Oh man, I'm stiff. I don't know if I said it already to this class. I said it to an earlier one. We had a really busy weekend last weekend, and I'm so stiff I can hardly move. My knee hurts, my back hurts. I'm feeling better every day, but boy, it's sort of rugged. Okay. So, we start row reducing A, but when we do it, we keep track of the elementary matrices used in each row operation. Okay? So, let's start with what's the first step we're going to do. Okay, what do we want to happen first? Let's review. We want 1 in the upper left. We already got it. Don't have to do a thing. Then what's the next thing we want? 0 below it. We got that. We don't have to do a thing. Next, we want the 2 to become a 0. So we are going to have to do an elementary row operation. Oh, by the way, I'm going to write I sub 3 right here. And that is 1, 0, 0, 0, 1, 0, 0, 0, 1. Okay, so the first operation we do is, tell me, -2 times row 1 plus row 3 is the new row 3. Going to do the same thing here. -2 row 1 plus row 3, new row 3. Okay? So, this step will be 1, -3, 0, that stays the same. 0, 1, 3, that stays the same. Now, do the third row. What do you get? 0, you say? Huh? Okay. -4. Perfect. Next. 2. All right. Going to do the same thing here to our identity matrix. Okay? So the top row, 2 rows stay the same. 1, 0, 0, 0, 1, 0, just like those top 2 are going to say. But now we do the row operation there. What does that give us? negative 2 times row 1, that's 1, plus row 3, which is 0. I mean, that's a negative 2. That's negative 2. Okay? And then negative 2 times 0, yeah. And negative 2 times 0, 1. Okay. So this is what we call our E1 now. All right. It is also necessary, I'm going to do another I3 here just like I did before. And this is 1, 0, 0, 0, 1, 0. The book doesn't do this. I just find it handy to do it. Okay, now we need to come up with E1 inverse. Now, to remember how to do that? Multiply by the opposite, whether the minus 2 is plus 2. So top 2 rows stay the same, 1, 0, 0, 0, 1, 0, and then it'll be 2, 0, 1. Right? Because that is 2 times row 1 plus row 3 is a new row 3. Okay? Now how you check this, like we did before you came in, you multiply these together, see if you get the identity matrix. Because if this is the inverse of that, when you multiply them together, you better get it. So you get 1, 0, 0. That's a 1. Good. 0, 0, 0. That's a 0. 0, 0, 0. That's a 0. This one. 0, 0, 0. That's a 0. 0, 1, 0. That's a 1. 0, 0, 0. That's a 0. See, these go pretty quickly. Then this one's the negative 2, 0, plus 2, that's a 0. Next, 0, 0, 0, that's a 0. And last, 0, 0, 1, that's a 1. Yeah. So that is the correct inverse matrix for that identity matrix. I mean, elementary matrix. All right. All right. Now we're not doing row reduction. Okay? Well, we are doing row reduction, but not reduced row reduction. Okay? The next thing we want is to have a 1 here, and we have it. Thank goodness. Okay? But what do we want next? A 0 below it. We don't care about above it, just below it. We're trying to get an upper triangular matrix. So we're not going to mess with the upper part, just the lower part. So that's going to be, how do we do that? Yeah, 4 times row 2 plus row 3 is the new row 3. Remember, that's the only elementary operation we can do is multiplying a multiple of one row to another, added to another row. Okay. Now, remember on this step now, let's go on and do that before I lose my place here. So that's 1, negative 3, 0, and I think that was that was a 0, wasn't it? I can't read my writing. 0, 1, 3, and then let's do that operation. You get 4 times 1 is 4 plus 0, no. Row 2. 4 times 0 is 0 plus 0 is 0. 4 times 1 is 4 minus 4 is 0. And 4 times 3 is 12. Plus 2 is 14. Okay. That's done. The elementary, this will be E2 operation, elementary matrix that do the same thing. Remember on this one, we go back to the identity matrix, not to the E1, but the identity matrix, okay, to the one on top, okay? And what does that have us do? You do the same thing. So it's 4, row 2, plus row 3 is the new row 3. And this is what goes down here. So 4 times 0 is 0 plus 0. Oh, wait, write the first two. 1, 0, 0, 0, 1, 0. And then the third row is 4 times 0 is 0 plus 0 is 0. 4 times 1 is 4 plus 0 is 4. And 4 times 0 is 0 plus 1 is 1. Okay? So that's your E2. What would E2 inverse be? Again, start with your identity matrix, not the E1 inverse, the identity matrix. 1, 0, 0, 0, 1, 0. Okay? Now, what operation do we do here? Basically, it's similar to what we did before. Okay? It's minus 4, row 2 plus row 3 is the new row 3. Just like this, only multiplied by the opposite number. Okay? So what would it be? No, 0. Okay, remember, we're using this one. Minus 4 times 0 is 0 plus 0 is 0. Minus 4 times 1 is negative 4 plus 0 is negative 4. And minus 4 times 0 is 0 plus 1 is 1. Okay. So that looks just like it. Now, if you have any doubt that that is indeed the inverse of E2, you can do this, because these have to multiply to be the identity matrix. 1, 0, 0 is 1. 0, 0, 0 is 0. 0, 0, 0 is 0. 0, 0, 0 is 0. 0, 1, 0 is 1. 0, 0, 0 is 0. And here's where we'll see if it really works. 0, 0, 0, that's 0. 0, 4, minus 4 is 0, 0, 0. Okay, that works. All right. Now we have our upper triangular matrix. And if you glance back on the previous, turn back to the previous page, you'll see, sure enough, that was the upper triangular matrix you had. That was the factor, LU factorization of A. 1, negative 3, 0, 0, 1, 3, 0, 0, 14. Okay. So we feel pretty good about that. Now, the reduced matrix U, that's the one we just did, is the upper triangular, and it follows that E2, okay, now what we just did, we started with A, and then you operated on it with E1, and then you operated on it with E2. That's the same as using those row operations that we did there, and that gave us our upper triangular matrix. Okay, U. Okay, now, if we started with A, okay, and first multiplied, and I wish I had left more room. I think I will. Okay. This is called cheating. Okay. Put my U way over there. If I were to multiply this on the left by E2 inverse, I'd have to multiply this on the left by E2 inverse. That then becomes your identity matrix, right? Then if we multiply that by E1 inverse, then these two multiply to be the identity matrix. Okay? So you have to multiply this by E1 inverse. Okay? Now, this is now saying, and then these are both identity matrices, so this just leaves us with our matrix A. And the matrix A is U times these things. Well, the product of those two had better be my L now. Let's see if it is. Okay? So let's do E1 inverse first. 1, 0, 0, 0, 1, 0, 2, 0, 1, and multiply that by E2 inverse, which is 1, 0, 0, 0, 1, 0, 0 minus 4, 1. Okay? I don't have much room to write this. So I think what I'll do, if you don't mind, because we're not using it anymore, I'll erase this one up here. I'll write it in there. I probably could have erased any of them, but I just wanted to hang on to it for now. Okay? So let's do that multiplication. And we think this should be L, the lower identity matrix. Let's see. So multiply those together. 1 plus 0 plus 0, that's a 1. Next entry, the 1, 2 entry. First row, second column, 0, 0, 0. That's a 0. Next entry, 0, 0, 0. That's a 0. So far, so good. Then the 2, 1 entry, a 1, a 0, 0, 0. That's a 0. The 2, 2 entry is a 0, 1, 0. That's a 1. And the 2, 3 entry is 0, 0, 0. That's a 0. And then the 3, 1 entry, third row, first column, 2, 0, 0. That's a 2. 0, 0, minus 4. And then 0, 0, 1. Let's see if that's what we got for L before. 1, 0, 0, 0, 1, 0, 2, negative 4, 1. Yes, that's exactly what we got before, had before. Okay? So sure enough, I'm sorry I missed that. They did that up there above. I skipped that part. But we still got it done. Okay. Now, all right. How are we doing on time? Did I not? Oh, here it is. If I ever carry my watch back. Whoops, are we out of time? I think we are. Okay, we went 2 minutes over, but there'll be no extra charge. Okay. I'm going to give y'all this one. Okay. Now, where are we? Yeah. Where we are is the procedure at the bottom of the page. I don't know. Let's go back. We'll do, that's paragraph starting with note, because I've already done the thing right after this thing we did here. But let's go back and note those multipliers. All right. Okay, we didn't get as far as I thought we might today, but we almost finished 2.4. Homework exercises here include any of the odds 1 through 7. They're all at Calc Chat. Either 9 or 11, they're both at Calc Chat. 13 or 15, they're both at Calc Chat. 17, any of the odds 17 to 21, they're at Calc Chat. 23 or 25, they're at Calc Chat. 27 to 33, they're at Calc Chat. There's a true-false 35, it should be at Calc Chat. There's a writing exercise, you can look at it if you want to, that should be at Calc Chat. 39 should be at Calc Chat. I think you can do either 41 or 43, they should both be at Calc Chat. And we'll hang up and do the rest of those next time, okay? Now, 2.5 we're really not going to do. I may talk through a little bit of it with you, but not a big deal, okay? It's not something I think that was called for in the course description. So my point being, I have the second test ready. Do you want to go on and get it? Because we don't do anything more than find an LU factorization, which we've just done. We're going to do more of them, but we've just done it. So now, I think I told you both, my work study student had put your first test in the shredder box, and we can't get to it because it's locked up. So I can't return your first test to you. I still got your research paper because she understood not to shred research papers, but she didn't understand not to shred certain current tests. I don't know why she shredded current tests, but she did. So anyway, that's over with. But this, I think, is the second test. You can get started on it. It's not going to be due for a bit yet until we finish 2.4 and whatever we do in 2.5. Okay? Good deal. So let's go on and